All right, Pat, thank you so much for joining us. Um, yeah, really excited to chat. Samara's very cool. When I looked into it, I didn't know about it before. I think we actually heard about you through Tom Mueller,
Oh, really?
the founder of Impulse. He was excited about you, and if the audience, for anyone who doesn't know, Tom Mueller, he was the mastermind behind creating the rockets for SpaceX, and now he runs Impulse, uh, one of the other most amazing space companies you'll see. But for him to talk so highly about Samara, it really caught our attention. And looking more into it, there's very interesting things to go over here. So, for listeners new to satellites, can you explain in plain language just what your company is building and why it matters?
Yeah, sure. So the foundation of Samara is based around an invention of my very good friend and co-founder Vedant. So he got his PhD from the University of Illinois, developing MSAC, which stands for Multifunctional Structures for Attitude Control. Um, And just to give, a little bit of a background here, almost every satellite in orbit is controlled by a set of spinning wheels, usually reaction wheels, control moment gyros, basically a heavy metal flywheel. And the concept is if you want to rotate to the left, you have to spin a wheel inside your satellite to the right. It gives you sort of an equal and opposite effect. The problem with those wheels is they're the number one failure point on satellites since they have bearings, they wear out, and that can end your mission. And they also shake, so they jitter your satellite. So if you have sensitive optics on board, which most satellites in orbit now do, that's a very big problem. So what MSAC allows us to do is instead of flying big, heavy reaction wheels in this pyramid formation, all we do is we embed little piezoelectric actuators right into the hinges of our deployable solar panels. And what this allows us to do is very precisely manipulate the panels very slightly up and down, left and right. And we do this very quickly and we vibrate little circular patterns into the satellite's solar panels. And this can trace a little circle in any dimension. And when you vibrate a mass in a circle, you get the exact same physical effect as spinning a wheel in a circle. So we're able to effectively eliminate the most problematic component on every satellite and repurpose and get dual use out of the existing mass that you're flying in your solar panels anyway. And then layered right on top of that is actually the foundation of this technology, which is active noise cancellation. So we listen at the center of the satellite using a high-speed accelerometer to measure the vibration profile there. And we're always doing an equal and opposite bump with the solar panels to make sure that platform stays about 1,000 times more stable than any wheel-based system could provide. Um, so that's the innovation. We're fundamentally changing the way satellites are built, changing the components that control them. And this has sweeping effects in a variety of areas, but most notably, it fundamentally flips a trade that everyone else has to make in satellite design, where if you think of it like a video game, you're creating a character, you pick your stats. If you want more power, that means you need more solar panels, but you're going to have to lower your agility because you now have a big flimsy structure and you can't rotate quickly in space or at all in some cases. We kind of give you the cheat code here. So you can increase your power, but you're also increasing your agility since our pointing control comes right from those same solar panels. So now you can have a very large, very agile space structure with enhanced stability. So I'll stop there, but that's sort of the core of the innovation here.
Gotcha. Now, when most people think satellites, they think of big clunky boxes, orbiting the Earth, um, all based on technology that's been around since the 50s, 60s. And when looking at yours, the Hummingbird, this very sleek, thin design. Can you talk us through how the bus itself is different than buses on the market today, and what you think this is going to mean for the future of satellites?
Yeah. Um, I think anyone in the industry knows that Flatpack is the future. Flatpack being, if you've seen a picture of Starlink satellites going up. They're very flat and they stack into the Falcon 9 or Starship fairing very efficiently. Most other satellites until today were, in fact, to an extent, still today, are still, yeah, these big boxy structures, but people are seeing that it's so much more efficient to get them to space when you can flat pack them. Now, ours has an advantage because if you see a picture of a Starlink satellite, you'll notice that they are almost exactly the thickness of these four wheels that are located on the corners of the satellite. And those are the reaction wheels. And you can't physically go smaller than that. The wheels have to be up on an angle and you're just never going to be able to. That's a hard limit. Everything else can be made flat. Electronics, fuel tanks can be slimmed out, etc. But those wheels are kind of a hard stop. So that's kind of at the core. Not only do we have fewer components in the center of our satellite, but we have fewer space limiting components at the center. So that allows us to thin things out and get even more packing efficiency out of our satellites.
Yeah. So you got these satellites, they're, advancements in power, agility, and, sleeker. What industries stand to benefit the most from this?
Yeah, so that touches on kind of our medium to long term vision here. I see three huge benefits, and we're going to attack one of them. I'll go in order though. Uh, the the reason MSAC was created was actually to benefit observation. So people flying sensitive optics. So Earth observation would see a huge advantage from us. Um, so that's just a matter of keeping a camera stable and still and not jittery and giving you a higher resolution image. Same thing for space-based internet and optical communications. Most satellites in orbit now are flying optical intersatellite links that shine a laser and transmit data at a very, very high rate. But it is an absolute nightmare to hold that device steady enough to get the laser hitting the other satellite that's also traveling 17,000 miles an hour. So um, that's the other area where we can offer an advantage. And the one we are personally going to go after is this RF space, radio frequency sensing, and a sort of passive listening, as it's known, technology. You could, if you had an antenna large enough and stable enough in orbit, pick up the Wi-Fi signal from my phone. But all the way up in space, it's a very, very weak signal, and most people can't resolve that. And the reason they can't is even if you have a large structure in space, you had to fold it up into a payload fairing to get it in orbit in the first place. Then you deploy it, and now it's this big, flimsy origami deployed structure. And the little perturbations in the panel and the antenna up there are going to just ruin your ability to detect these signals. So with MSAC, we are uniquely capable of actively stabilizing that large structure. So on the reverse sides of our solar panels, we have antennas. That's not new. People have done that for a while, but we will be the only ones with a stabilized structure. So with a 10, 15, 20-meter long satellite with our wingspan around that size, we can actually pick up incredibly weak signals. That's going to allow us to do a ton of stuff spanning from commercial to civil to defense, with the defense space being the largest possible customer there. And I'm happy to dive a little deeper into that as well.
Yeah, let's dive a little deeper. I'm curious how the Hummingbird integrates with the DoD space defense strategy.
Yeah, so the idea we have is so we're working with a friend of ours who happens to be an expert in radar technology and RF systems. Got his PhD in exactly this problem. It's that if you can detect a weak enough signal, well, we're always blasting the Earth with RF signals from everything from Starlink, but more importantly from GPS, GLONASS, Galileo, all these global navigation satellites are covering the Earth in a constant signal. And you can use that as your radar signal. It's a known signal. So if you detect it reflecting off an object, you can calculate the sort of Doppler shifting of that signal and track objects in the atmosphere, especially very high speed objects. Um, so people could do that now if they had a stable antenna. So we basically unlock that. It's a passive system that cannot be detected and cannot be jammed because we are not emitting a signal. We are just listening to the Earth.
Got it. I have a question here from the audience, and audience members, feel free to. There's a Q&A section at the bottom. Just feel free to write in any questions you'd like, and we'll get to them. But the question I have here is, what effect, if any, does this have on rotational velocity?
Yeah. So what our system does is it gives us an incredible amount of torque. These actuators in the panels produce a tremendous amount of force, and then you kind of have a lever arm that is the distance between our panels. So what we can do is almost instantaneously bump up to our max slew rate, and then almost instantaneously come to a stop. What most systems do today, they have very low torque, so it'll be a slow ramp up to a high speed and a slow ramp down, and then you kind of wobble until you settle in on the location you actually want to be. So what we do is we basically turn it into a step. It's, bump up, go over, down, and you're ready to go. So while depending on the size of the solar panel, we might come in a little lower on our top speed. Our overall agility is going to be higher than most systems.
Very cool. Now I'm thinking about this. With this packed, sleek design, uh, well, how big is it in comparison to an everyday object? What do these things look like, and how much do they weigh? Do you need Starship to get them up? Do they go up on the Falcon 9s? How many can you pack in there?
Yeah, we're planning to so we're sizing it like most other bus providers for the transporter missions in the short term. So if you're familiar, the transporter missions are SpaceX's rideshare. We're sized for like an Espa Grande. If to try and I'll just give everyday terms. Size of a coffee table, kind of folded up. So we're planning for two sizes. So this Hummingbird behind me, we want that to be in the 100 to 500 kilogram range. And then we're planning on a larger form factor, which is currently we're referring to as Kite. Kite will be up to 2,000 kilograms. And that's designed for the cake topper, which is the larger set of available payload space in the transporter missions. So yeah, we'll have one that's between 500 and 2,000, and then one that's under 500 kilograms.
Cool. Can you tell us where you are right now with terms of traction? Like what's happened in the past 2 years, and what do you have coming up in the next 12 months?
Yeah, so we didn't really kick things off until February of last year. That's when, Vedant and I stopped moonlighting and went full time at Samara. So traction wise, yeah, we've won a number of government contracts. We're up to, I think, 6.2 million in government contracting. Just won a tactical funding increase, a TACFI, on top of our direct to phase two SBIR with the Space Force, bringing that total contract value to about 3.25 million. Just won a phase two SBIR with the National Science Foundation for another 1.25 million. Just got a phase one SBIR with NASA, which we're excited about because now our foot's in the door. And then several months back in the spring, we closed a pre-seed round for around $2.25 million. Um, Traction wise, last year alone, we were able to secure about $800 million in commercial letters of intent, signaling interest for about 110 of our Hummingbird satellites and around 60 of our MSAC control systems. Um, we are directly partnered with Planet Labs on one of our SBIRs with the goal of eventually providing their control system for their next generation of Earth observation satellites. So we're seeing a lot of interest in the industry.
Yeah, I can imagine a lot of people are very interested in this. When do you start putting these up into orbit?
Yeah, so as you know, I think the reason Impulse Space was excited by us is we were able to close a pre-seed round in February, and in May, we delivered and integrated a fully built-out, tested payload, demonstrating our MSAC system. And basically, it's going to show up like two of these hinges and a counterweight, but instead of a panel, it's just a dummy weight. So we'll be shaking this weight in the same way that we would be shaking one of our panels, with the goal of trying to rotate the spacecraft up there a little bit. Um, so yeah, we were able to put that together in about 3 months, which we're really proud of. We showed up first, we integrated first. So amongst all the other payloads, we're also like to brag about that. But so that's launching in October. And then as far as getting the actual Hummingbird in orbit, we're targeting a Q1 2027 launch at this point. Um, there's a chance to bring that timeline in, but these launch slots fill up pretty quickly. Yeah, so the LOIs we have specify a first delivery of a first unit at the end of 2027. So that's sort of the goal we have in mind.
Gotcha. Uh, I see another question from the audience. Is this patented? And what's the moat for this?
Yeah, MSAC is fully patented. So the technological moat is that this is not easy. Not only is it patented, but it is difficult. Vedant, spent his PhD creating the first iteration of the system, and we have spent a lot of time, both just as part of the company R&D and as part of SBIR contracting, developing the system, creating tools to allow us to quickly iterate and customize the advanced titanium flexures that are used to amplify the motion of those piezo crystals. So um, even if someone decided to ignore the patents, they are years behind us in terms of development.
That's awesome. Now, I'm thinking about this, like, what does a constellation of hummingbirds in orbit enable that we don't have with legacy satellites today?
Glad you asked. Yeah, so we are hoping for a constellation of around 120 to 180 to give us full global coverage. So a few of the things you can do in increasing order of interest is, you can talk to low power devices, IoT devices on the ground, little weather stations in the middle of nowhere, ships in the middle of the Pacific with no infrastructure for communication, just collecting little bits of data without requiring them to carry a big antenna or consume a lot of power. You're talking just your regular cell phone type thing. Um, what else we can do is estimate populations. So we can look at an area on the Earth and we can't decrypt all the signals, but we can see, oh, there's noise in this region that indicates there's about 10 cell phones. It's like, oh, well, usually there's nobody there, but we can assume there's 10 people with cell phones in this area now. Um, you can turn the antennas the other way. We can do radio astronomy and get insights into the origins of the universe, measuring pulsars. We can enable a better data link to the cislunar economy. Um, Again, right now, everyone going to the moon, the commercial moon space is blowing up. A commercial company landed on the moon, which is incredible. But everyone right now is relying on NASA's Deep Space Network, which is notoriously congested and you have to fight for time on it. Well, now satellites going to the moon can just communicate with their, off the shelf regular radio, and we can actually resolve that signal from low Earth orbit and relay that data for them. Um, but then, the biggest market is going to be defense. So, as I said, staring at the Earth, listening for objects, things like, oh, wow, there's a very high speed object moving through the atmosphere right here based on Doppler reflections that we're hearing from GPS satellites, So, there's a huge range of applicability of that constellation.
That's really cool. I'm just thinking about, all these hummingbirds up there and all the things we'll be able to do. Um, I'm curious, when you've been doing this and getting these up there or getting these built to go, has there been any unexpected lessons that you've been learning while in the process of building these or in running tests that makes these different than normal satellites, and they have to maybe adapt to you know work more properly. Um, I'm curious because there's got to be some other uh, directions that a giant bulky satellite goes than what you do, because what you do is very different just by looking at it. And maybe after this question, we can transition into taking a look at the factory. And if you have any of these, I'd love to check one out.
Yeah, we have a ground unit of our Hummingbird sort of hanging by a crane in the lab. I can show you. It's not space rated. It's more of a proof of concept. So it's got, two panels with our MSAC actuators, and we'll be able to show it rotating around. I don't think it's connected up right now to give you a rotational demonstration, but yeah, I can show you around that. In terms of lessons learned compared to boxy satellites, it really is just kind of a matter of leaving out the wheels. Everything else will more or less look the same. Early on, it's going to be a lot of third-party components building it out, and will become increasingly vertical as we go. My co-founder Vedant is the smartest person I know, and he can't wait to develop his own Hall effect thruster. And our head of RF and avionics wants to create his own radio. Uh, yeah, it'll look mostly the same as in terms of the guts of the satellite, except for the control system. Lessons learned. Keep an eye on your supply chain. Always have a backup. And oh my God, launch vibrations are way more of an issue than people think. So we've managed to make our MSAC hinges basically bulletproof at this point to survive like a harsh launch environment.
Wow, crazy to think about, just a launch vibration of just something with all these stacked in there going up with such velocity. Yeah, is there any chance we could take a look at the one you might have hanging?
Yeah. Let me see if I can mute and turn off my camera the right order.
Uh,
All right. Oops. Get out of my phone booth. There we go. Okay. Can you hear me okay?
yes, we can.
Alrighty. Cool. So, hey Vedant, I'm taking the crew on a walk here. So we just moved into this 11,000 square foot facility. So we're still, settling in, got our phone booths set up over here. Vedant is behind me, and we have our summer interns here, Avanish and Alex. Avanish's last day is actually today. Uh, so walking over, we have a much larger build area than the last time. We have about 5,000 square feet dedicated to just building out our satellites. The other half of the facility is dedicated to office space. So this is Hummingbird hanging from a crane right now. We actually call this one Flappy Bird. It's not space rated, but we have our mass offloading system and our ability to sort of rotate it without friction by hanging it from a thin string. But yeah, so right here we have a set of two of our MSAC flexures. There's two at each hinge point, and this will be able to vibrate these outer panels to give us a rotation. As I said, this is just the control system. This doesn't have any of the usual satellite guts connected to it. Any questions there before I show you something else?
No, it's really cool. Yeah, I was curious with the propulsion systems and where you're keeping the space compute system. Are those developed internally in-house, or what are you putting on these satellites, and where are those coming from?
Yeah. Let's see. Sorry, I'm trying to. There we go. I think the audio was a little low. Could you repeat that? What's different on the satellites, did you ask?
Yeah, I'm curious with the propulsion system and the compute system. What do you have going on them? Are you building them internally? Um,
Oh yeah,
yeah,
most of the components are third party. Our MSAC hinges, everything that is all custom in-house. So we're doing all the assembly in-house. So early on, our radio will be a third party radio. Our prop system will be a third party Hall effect thruster, etc. Yeah, that answer your question?
yeah.
Cool.
And the for the Earth observation that you do, are there special cameras that you're putting on these? How big are they?
No, we don't intend to actually do Earth observation.
Uh,
We can market the satellite buses to somebody doing EO, but that's not currently in our roadmap, at least not yet.
Understood.
Yeah. Yeah, the Hummingbirds we want to fly are looking at the RF radio frequency. So it's basically just our stock antennas going up there on the backs of our solar panels.
I have
Uh,
another. Oh,
oh yeah,
so
another question.
there's another question from the audience. Is there a working proven example of this operating in space right now?
No, it's on the side of the Impulse Space bus at the moment, waiting to launch in October. So, and I can show you the payload right here. And I think Vedant has this set up. By the way, this is Vedant. Hey.
Hey,
Let me make sure this is in frame here. This is our what we call the Cicada payload. This is a ground unit of exactly what is flying on the Impulse Space bus, minus some of the harnessing and everything. Um, so as Vedant is pushing on the payload here, we have this screen showing the computer measuring the displacement of these flexures. So this is one of the ground units that we use to test out the system, and if we make any software changes, we can upload that to the one on orbit and do some new testing that way.
got it.
With
Um,
navigation stems.
is there any plans in the future to maybe have these being, lunar orbiting, orbit Mars, things like that? There may
Yeah,
not be much of a need to do that right now, but later in the future, it very well could be, a big need to have these there.
absolutely. And I mean, going to the moon, especially with our RF system capable of communicating more easily in deep space, that is certainly a possibility. We design everything for MEO geo orbit where there are harsher radiation environments. So really, what you all you have to do is retrofit the satellite. You can't use the Earth's magnetic field anymore. We'll have to have some extra thrusters, all the same modifications that everyone else will have to do. But yeah, you absolutely could send a Hummingbird to the moon.
Um, Transitioning back, I'm thinking about this 800 million you have in LOIs, and you're talking about how this is still very new idea that you got going this year. So I'm curious how those keep consistently rolling in. Were you at 700 million like a month ago, and they just keep stacking on? And what industries do you see most excited and are setting up these LOIs?
Yeah, it's kind of across industries. So they are we've kind of put a pause on our pursuit of LOIs. They're not as helpful at this stage in the company. Most of those were gathered last year. It is across industries that we're seeing interest. We have a lot of interest from one of the primes. I'm not allowed to name them, but they signed up for 40 of our kite, the larger form factor hummingbirds. Their interest is purely in their ability to quickly launch flat-packed GPS replacement satellites. They don't care about jitter. Planet Labs signed an LOI with us because they do care about jitter. So they want to stabilize and have a more agile spacecraft. Loft Orbital signed one of those LOIs, and their customers down the line are complaining about jitter and how flimsy the platform is, and they want to do more sensitive optics. So Loft wants to have more stable spacecraft on hold. So um, it's kind of across industries here where people are interested. It's the problem of jitter and agility is something most people don't think about, except for the few engineers designing the satellites who are frustrated by legacy systems.
Uh, um, well, this is all growing so fast. Can you tell us a little bit about this? The team's development. How big were you a year ago compared to now, and what's it like trying to find that talent of these, you know, super high IQ people, very exceptional in this industry where, it's blowing up and everybody wants to try to get the top talent.
Yeah. Well, I'll say here's our very sparse employee area. So we have every all of our desks pushed off to the corner because we're building some conference rooms off to the other side here. But we're sized to scale to 30 plus employees here. A year ago, it was three of us. We would have just hired our first. Oops. I was going to go back into my booth and it's going to be an echoey nightmare. So let me mute. Okay, sorry
Finish
about
this
that.
up.
Is that coming through okay?
Yes, it is.
Alrighty. So yeah, a year ago, there was just three of us. Now there's 10 if you we have our 10th employee starting on first week of September. So if you don't count the interns, or if you do count the interns, that'll put us at 12. So hiring in the Bay Area, it's yeah, really easy to find great software engineers, for example. It's very easy to find mechanical engineers. Electrical engineers are the toughest part, but we have a, pardon me, 'cause I'm just gonna, this other call was echoing in the background. Um, yeah, we have a very employee forward culture here. Um, I see kind of a problem in the space industry in terms of work culture. A lot of companies do have what could be viewed as a very toxic work environment where you're expected to burn yourself out effectively until you just move on to the next gig. Um, we treat our employees very well. They are my number one asset. If you have the right employees with the right motivations, you're going to be able to go a lot further than people who just, mistreat them and force them to work crazy hours all the time. So yeah, we attract the top talent by providing them the top of the line benefits that we possibly can, all the healthcare, vision, dental, life insurance, 401k, unlimited PTO, et cetera. And what I've found is employees are not abusing that. They are motivated by the mission. So again, we got that cicada payload out in 3 months, and I didn't have to crack the whip. These guys knew the significance of that mission. They made it happen. They came in, they got it done. And that's the kind of talent we're after.
Very cool. I like that. Another question from the audience. What are the likely paths to exit?
Yeah, so we've thought about that. If you asked me a year ago, I'd say probably not an IPO, just because we saw the incredible backfire of all the SPACs from, 5, 6 years ago, or God, was it only 4 years ago? Either way. Um, Now, people are successfully exiting into the public market. Was it Firefly just yesterday had an incredible exit? So that is a possibility. But we also recognize that we have a very disruptive piece of technology going into a market with giant players like the traditional primes like SpaceX. Um, this is a system that is ripe for an acquisition, I think, So 5, 6 years down the line, maybe somebody sees the incredible value that Hummingbird's providing and wants to do an acquisition. So those are both equally plausible routes at this point, I think.
Got it. And can you give us sort of a idea of the revenue streams you have going? You mentioned earlier, you have customers using your service. Um, I'm curious how it's split between, are you selling the actual satellites to people? Are you selling the service? the data. And I'm also curious, how many of these are government, how many of these are commercial space?
Yeah, the space industry kind of had first it was all government, and then the commercial boom happened a few years ago. But now I feel like there's kind of a swing back to the government. Well, governments worldwide are investing more and more into space, so that's taking off again. Um, so a year ago, I probably would have said 50-50 split, commercial government. Now it's probably like 40% commercial, 60% government in terms of our potential markets here. Um, yeah, the focus in the short term is selling hardware. So we're developing the Hummingbird bus. That has to happen no matter what, and we can market that as a generic piece of hardware that people desiring a stabilized spacecraft can purchase. But the goal in the medium term in 3 years from now is to start deploying a massive constellation of our own satellites and then sell the data. So basically, we could be a service. We can act as a data relay with a subscription model. You can actually, wire in sort of a back door and hand the government the keys and say, hey, for X number of dollars per satellite per year, if you need to just take over and drive for a minute, you can do that. And that's a model that other companies are exploring right now as well.
Oh, sure. I had another question that was said to me. I know we discussed it a little bit earlier, but with the increasing lunar activity driven by, the Artemis initiative, are there any use cases for the Hummingbird task data relay?
Um, let's see, for specifically for the lunar economy.
Yeah.
There certainly could be. First of all, the further you go from Earth, the dollars per kilogram goes up very rapidly. So, it's cheap to get satellites into low Earth orbit, but when you're going to geo, when you're going to the moon, every kilogram becomes more and more and more expensive. So just the fact that we are leaving these big heavy wheels at home and not taking them with us is going to give us a huge economical advantage, just purely in terms of the mass and volume efficiency of our satellites. Um, in terms of, usefulness of this RF play that we're after, uh, I see mostly a just data relay service as the primary benefit for the moon. But as I said, we're opening up markets that people don't even know exists yet. So it'll be interesting to see what sort of innovations come along once this capability is available to the market.
Not too. How long do these satellites stay in orbit? And at the end of their lifespan, what do you do with them?
Same as everyone else. They'll either, I think they'll need to be deorbited, or if it's in a high orbit, unfortunately, everyone gets shoved into a graveyard orbit, and kick the can down the road for the next generation to deal with is the current model. Not our model, but what society has decided. But um, yeah, in terms of end of life or lifetime, we're targeting about 10 years in low Earth orbit and 7.5 years in MEO and GEO and beyond. Um, the nice thing about our system is it's incredibly resilient to radiation. So um, when that's the only change, you don't really have to, there's rad hardened components you can use to extend the lifetime of your satellite.
Uh, what's the timeline on the constellation?
That's a great question. This is the RF constellation is still, we work every week towards logistically planning out, okay, what's the next move here? I imagine we'll start getting those up in 2028, 2029. And then it's a matter of, how quickly we can scale that to over 100 satellites. But we imagine we're going to get some early demonstrations from our first mission because we're still, no matter what, we're flying those antennas. We just aren't going to fly a 20-meter Hummingbird on our first mission, but it'll still give us a relevant demonstration of that tech.
Got it. Looking at this market space with all these new satellite developments and bus technologies going up. Um, what the type of technology that exists today, or maybe company, would you find to be maybe a competitor, direct competitor? I know your technology is so differentiated, and the services you provide become, much more powerful. But where do you find yourself in this ecosystem?
Yeah. So we know for a fact that we have something, unique to offer the market. We're giving you a satellite that's, better, faster, and cheaper. The unfortunate reality for us is that buses, the bus market is growing, but so are the number of competitors. Everybody's coming out with a new bus, a new flat pack design. You see that from Rocket Labs. Even Maxar is developing their own satellite platform now. You have Apex, Blue Canyon, Aerospace Lab, all of them developing buses. And what we're seeing is a kind of saturated market, especially with other people all trying to go vertical and in-house their own satellites. So it's a tough market, but we have something truly unique that no one can touch us on to offer. But that is part of the reason why we're so excited to deploy our own satellites and keep it in-house, keep our costs low, and just do it ourselves and target the much, much, much bigger market, which is, for example, you have this Golden Dome effort. They're pushing for $100+ billion budget just for that um, coming up. And that dwarfs the satellite manufacturing market. And we're seeing estimates that, if they truly want global missile coverage, it'll cost hundreds of billions of dollars. So that's the opportunity we're after is, maintaining US space superiority, and targeting that market and enabling that lunar economy and sort of keeping the satellites in-house is going to be, I think, the longer term better model for us.
Nice. And you mentioned Golden Dome earlier. I'm very curious. How does Hummingbird fit into that? I'm sure there's lots of things, but do you have a plan of action of pursuing Golden Dome opportunities? Have they approached you? What kind of service would the Hummingbird do up there for Golden Dome?
Yeah, so they, the Defense Department likes to refer to the kill chain. And it kind of, I forget what step one is, but right in there, it's tracking. So it's missile protection. It's find a missile or a threat, identify it, track it, and then deal with it, intercept it, whatever, or take a course of action. The tracking part, that's what we're after. That's where current technology has some gaps. There's infrared sensors that rely on that thing generating a lot of heat to track it. And those are multi-million dollar exquisite sensors from industry primes. We're talking about silently tracking that same missile with off-the-shelf technology, patch array antennas, software-defined radios, tacked onto the back of a cheap Hummingbird that's operating completely silently and relying on other signals to light up the scene for us. So we can't be detected, can't be jammed. So it's going to be an overall better system for them in that regard, and that's the market we're after. Yeah.
Uh, Thinking about this, I'm sure that the aha moment was a very cool experience of realizing you had something special and new. But I'm curious, has there been any crucible moments where there was a major barrier that you had to overcome that maybe you thought couldn't, or kind of roadblocks that you hit along the way? I know it's still early in your journey, but is there any moments you look back on saying, that was such a critical moment and we beat it and we're moving forward and we're gonna be fine?
Yeah, that would have been a great question for Vedant, because most of the technological moments like that are mostly hidden in the lab. I'll say in terms of development, just as an example, while we were developing that cicada payload, incredibly tight timeline. The first time we sent it to Launch Vibe, um, well, first of all, we were told we had to vibrate it to a much higher standard than what you'd actually see in launch, but it destroyed all four of our flexures thoroughly because our launch locks needed to be iterated, and we iterated on it in 1 week And 2 weeks after that, we went back to launch 5 and had no damage whatsoever. So things like that, where it's like, oh my God, we just, launch is going to kill us. Oh, wait, no. All right. We worked hard and we solved that problem, So that's the example that comes to mind there.
Nice. Yeah, the being able to iterate things really fast, that's always such a you know, key thing that all startups really need to have. I'm
Yeah.
curious if you're still doing iterations now, or if you're just you know, really building out that final model to fly in orbit with Impulse.
Yeah, always iterating. So we have very talented structural analyst from Maxar. He's our only remote employee. We prefer most people to be on site, but this guy's really good. So he works out of Texas, and he's always doing an analysis of our flexures to iterate on how we design those, how we encapsulate these piezoelectric crystals. And you can kind of see it here, this little stack is represent this is off the shelf. We don't publish renders of our actual design because that's very much proprietary. But these custom titanium enclosures that go around these piezoelectrics are incredibly sensitive to little design perturbations, and we're maximizing the performance using those. And that is something we're always iterating on, making them more efficient, making them more resilient, etc.
Awesome. Very cool. Okay. Well, I think we're wrapping up on time now. Pat, I want to thank you so much for, giving us your time and chatting with us. Very interesting stuff. Learned a lot. Uh, Audience learned a lot as well, I'm sure. Uh, Going to be at Small Stat Convention next week.
Yeah, we're the team's going to small sat. So me, Vedant, our director of biz dev, and our chief of staff will all be in attendance, trying to uh, tag team all the different booths and everything. So if you want to chat, I'm happy to tag up there.
Very cool. Yep. I'll be there. So we'll chat later and catch up.
Great.
Uh, all right. Well, Pat, thank you so much for taking the time to join us and speak. Um, yeah, if the audience has any more additional questions or ways they want to get in touch with you, what would be the best way of reaching out?
Yeah, you can. You have my email, so
Yep,
feel free to share that if they want to ping me via email. Happy to answer any questions.
sure. Yeah, so audience, any questions, just reach out to the Balerion team and we'll get you through.
Yeah,
All right,
and
Pat.
if you want to, yeah, it's just Pat, P-A-T, at samaraerospace.com. So super easy.
Awesome.
Yeah,
All right, Pat. Well, thank you so much for joining us. And I look forward to seeing what Samara does in the future.
absolutely. Thanks for having me. It's great talking.
Thanks. Take care, all.
See ya.